An approximate model of the motion of an international space station is that it travels at a speed of 27,600 kilometers in a circular orbit at an altitude of 400 kilometers. So to visualize a question like this, it's not bad to draw a picture of what's happening. So we're going to draw a globe here, try to draw North America as best as possible, and so there we go. Wow, okay. Here's Europe, Africa. Okay, and a little bit of Australia there, some islands. Make sure Hawaii's on there. Perfect. Oh, if you're wondering, yeah, a little bit of Antarctica in there. You want a big island of Greenland, there you go. There you are. You are here. There we are. So what's happening is we've got some sort of international space station. I think they all look like this, right? Some sort of alien in there. So there's our International Space Station hovering at 400 kilometers above the Earth. We know that, so here is this, here's a lava there right in the center of the Earth. We know the radius, and then this is another 400 above that, making that distance in total 6,800 kilometers. And this space station is traveling, wow, that's not a very good circle. Here we go. There, that's looking better. It's traveling in a circular orbit around the Earth. And fast, 27,000 kilometers per hour. So now in part A, we're visualizing this. We're imagining that space station drawn to the center of the Earth, making a radius, and it's traveling for 40 minutes. So after 40 minutes, maybe it has gone that far as an estimate. And we want to find out, to the nearest tenth of a radian, what is that angle that it's traveled. How much will that line segment have rotated after 40 minutes? So looking at the diagram, this black line where the space station has traveled, what do we call that? It's part of the circumference, right? And if it's part of the circumference, what did we call part of a circumference? An arc length. We have a formula for arc length that we've already developed. The formula in radians was this. The formula in degrees, remember we said, well, it's just a portion of 360 multiplied by the circumference. Are we dealing in radians or degrees here? We're dealing in radians, so we can use this formula on the left. We want to find the angle, so we're trying to find theta. Do we know the radius? Yes, it's 6,800. Do we know the arc length? Kind of, not exactly, but we can figure it out. How would I figure out, if we know how fast it's traveling, how far has it gone in 40 minutes? 27,600, because that's how much it would travel in 1 hour. But I'm going to need to multiply this, well, not by 40, because it hasn't been 40 hours. What do I put in here? Right, 2/3, because if you think of 60 minutes in an hour, 40 out of 60 minutes is 2/3. And if we multiply this on our calculator, 27,600 multiplied by 2/3, 18,400. That's the distance it's traveled already. So maybe I'll label this a little bit nicer. What did we do here? We found the arc length because we knew how fast it was traveling for 40 minutes, so we could figure out how far it traveled in 40 minutes. Now that we have that value, we know the arc length, we know the radius, so in this formula, the only thing we don't know is theta, and that's what we want to find. So we can plug in for the arc length, 18,400. We don't know theta, but we can plug in 6,800 for the radius. And when we divide both sides by 6,800, everybody familiar with their calculator? If they have an answer from before and you just hit divide, it takes that same answer so you don't have to rewrite it. So I want to take that 18,400, divide it by 6,800, and I get approximately 2.7 radians. Which kind of makes sense if you think, remember the definition of a radian is each radian is one radius along the outside edge of that circle. So if I go 6,800 once, 6,800 twice, to get up to 18,400, 3 would be too much. But it needs to be more than 2. So that kind of visualization and estimation to say, does 2.7 make sense? Because sometimes you're doing math, right? Sometimes you're doing math and you want to go 18,400 divided by 6,800 and you accidentally hit the wrong button. And you're like, wow, that's a big number. And you might not know what you did because you didn't realize you hit the times button instead. But if you do a little bit of an estimation, 125 million of these along the outside edge of the circle, that would be too much. That would be insane. You would be going really, really fast. 27,000 kilometers per hour wasn't fast enough for you. So there we have an angle. Now we're not going to do part B. Not going to worry about that. You don't need to see part B for doing the homework on this one. Part B connects to last year's math with the cosine law. So if you want to do it on your own, you can read the example beside. Remember, it's just using the cosine law in radians instead of degrees. So if you want to read that off to the side on your own time, that's fine. But we're not going to do that right now. Right now, we're going to work on questions 8 and 9. Most arc length questions come up as situational word problems. A lot of them do. So that's why we did this question. The ones in your homework don't involve space stations, but you can keep drawing UFOs if you like.